All right, this is 5.3 part 2, and we're going to talk about the first derivative test today. We're going to start off with something called Fermat's theorem. Don't worry about knowing the name, I just want you to know the concept. It's an important concept. Now what it says is if you're looking for local minimums or maximums for some function f, they always happen at the critical numbers. Now remember, we spent all of part 1 talking about how to find those critical numbers because that's a real important concept, and this is really why. Now before we move on, I want to make sure you understand that does not mean that every critical number is automatically a minimum or a maximum. It just means those are the only places that can happen. So for example, I remember in part 1 we had a problem. We were finding critical numbers and the answers were 0, -1, and -2. Now what that means is about the original function itself, if you're looking for local minimums or maximums, those are the only places they can happen. Now it doesn't automatically mean that each one of them is a minimum or a maximum. It just means those are the only places you even need to check. So let's go back to one of the very first things I told you guys about the derivative. I said one of the things the derivative tells you is when a function is increasing or decreasing. And it's basically a matter of positive or negative. Wherever the derivative is positive, the function is increasing, and wherever the derivative is negative, it's decreasing. Now, that's going to actually give us the true definition of local minimums and maximums. So we said in part 1, I gave you kind of the visual description of them. I said if you look at just a little piece of the graph, if it's the maximum on that little piece, then we call it a local maximum. Well, here's the true definition of the two of them. A local maximum happens wherever the graph changes from increasing to decreasing. And a local minimum happens when it changes from decreasing to increasing. So for example, if we had, I'll draw a nice simple graph for us. Let's say we have this graph right here. Now this red point right here, that is a local maximum. Now the real reason it's a local maximum is because imagine a point moving along that graph from left to right. It's increasing, 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 up, 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 right until it hits that point there. Now as soon as it passes that point, the graph is now decreasing, down, 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 until it gets to this point right here, which is the local minimum. Now once it passes that point, it starts increasing again, up, 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 up. So that's the true definition of a local minimum or maximum. It's where a graph changes from increasing to decreasing or decreasing to increasing. And that's going to be an important part of what we're getting to, which is the first derivative test. All right, so here is the first derivative test. These are the steps to doing it. Step 1 is what we did part 1. You know, the entire day, the entire part 1 of 5.3, we focused on finding those critical values or critical numbers because they're very important in the process. So we're going to do that again. Now, if you need to review or refresh on how to do that, just go back and watch the part 1 video. We talk about it a lot. Okay, step 2, you're going to make a number line and you're going to use the critical values to break it up into intervals. Then what you're going to do is you're going to take a number from each interval and test them in the derivative, in f prime. Now when you're doing the test, you're actually plugging the number in. So like let's say I'm testing the number 5. So I take my derivative f prime of x, I plug in 5, I see what I get. Now I don't really care about the number part. All this test requires is that I check whether I'm getting a positive number or a negative number because I want to know if that function is increasing or decreasing. So let me give you kind of a little partial made-up example here. Let's say I draw my number line, here's 0, and on to the right I have 1, 2, 3, 4, 5, and it keeps going. To the left I have -1, 2, 3, 4, 5, -5. So that's what we mean by a number line. It's like the x-axis basically. Now let's say, I'm going to just kind of make up some numbers here. Let's say one of my critical values is -2, and one of them is positive 3, and one of them is positive 5. So I've actually, by having 3 critical numbers, I've broken it up into 4 intervals. So what you want to do is test a number from each interval. So my first interval is everything over here. Basically everything less than negative 3. So I can pick any number I want over there. I can pick negative 4, negative 5, negative 100 million, anything less than negative 3. So let's say I plug in, or negative 2, sorry. So let's say I plug in negative 5 and I get a positive answer. So what I'm going to do is I'm just going to put a plus here to show that the derivative is positive in that interval. And then I pick a number in my next interval. It would be something between negative 2 and positive 3. So let's say I pick 0 and it comes out negative. So I put a minus there for negative. Now my third interval, I would probably pick 4. That's the only whole number in there. Although, just so you guys know, you don't have to pick a whole number. I could pick 3.1 or 4.9 or something like that, but whole numbers are the easiest to work with. So let's say I test 4 and I plug it into the derivative and I get a positive number. So I put a plus here. And then I test the last interval, anything bigger than 5. Again, I can pick 6 or 10 or a million. And I'd pick a number, let's say 6, and I plug it in and we'll say we get a positive number again. So what we've done is we've determined where the derivative is positive or negative, which tells us where the derivative is increasing or decreasing. Now, by seeing where it changes from one to the other, that's going to give me my minimums and maximums. And that's really the first derivative test. So let's come back to this picture in a second, but I want to talk about that. So we're going to use the definition that I just gave you a couple slides ago of local minimums and local maximums. Basically, anywhere you change from a plus to a minus, which means the derivative is going from positive to negative, which means the function is going from increasing to decreasing, that's a local maximum. The opposite is a local minimum. So anywhere you change from a minus to a plus, you have a local minimum. Now, just as a reminder, not every critical value is a minimum or a maximum. Sometimes you have some that are neither. And if I go back to that picture I had, I'll draw a quick sketch of it. We had something kind of like this. We had 3 critical values. I'll just put them in like this. And when I did my little pretend test, it went plus, minus, plus, plus. So what we're really saying there, what this graph is doing, the plus means increasing. So right here the graph is increasing. And then the minus means decreasing. And then the plus means increasing. And then the plus means still increasing. So by drawing in those little arrows that I just drew, you can kind of see the shape of the graph. And you can see that right here, that would be a local maximum. And right here, that would be a local minimum. And right here, it would be neither, because it was increasing and it just kept increasing right through there. It didn't turn. And that's really how the first derivative test works. Anytime it changes from a plus to a minus, you have a maximum. A minus to a plus, you have a minimum. And if it stays the same, you have neither. So if the plus minus sign doesn't change, which is what happened right here, if it goes, even if there's a critical value there, but it starts positive and stays positive, or starts negative and stays negative, then it's not a minimum or a maximum. Now the last thing I want to mention here, it's kind of a weird little thing that can happen. In order to be a minimum or a maximum, the critical value has to actually represent a point. So sometimes you get a critical value where there's like an asymptote on the graph and f of c is undefined. That can't possibly be a minimum or maximum because it's not even a point. So I'll show you in the work when it comes up. You'll notice because there's a point where you try to plug in the x value to see if it's a minimum or a maximum, and it comes out undefined and you realize it's neither. But let's go ahead and do a couple examples here. So we're going to find all the local minimums or maximums of, and the directions are actually on the bottom here. It's x to the 4th minus 8x squared plus 11. All right, so step one, well, let me start with the function. X to the fourth minus 8x squared plus 11. Step one is to find the critical values, which we did in part one. That means, number one, find the derivative, f prime of x. And this is a nice easy one, it's just power rule. So I multiply by 4, lower that exponent to 3. For the middle term, I multiply by 2, lower the exponent to 1. And the 11 is basically going to disappear. The derivative of a constant is 0. So f prime, nice easy one to start us off with, 4x cubed minus 16x. Now to find critical values, I'm looking for places where this is either equal to 0 or undefined. Now for this one, since it's not a rational function, it's not a fraction, I don't have to worry about undefined. This is defined for all real numbers. So all I have to do to finish this part of the question is set it equal to 0 and solve. And I think I'm going to solve by factoring. I'll start by factoring out of 4x. And that would leave me with x squared minus 4. And the x squared minus 4, that factors in, that's difference of 2 squares. So that factors into x plus 2 times x minus 2. And that gives me critical values of, I get a 0 from that x that I factored out. This one right here gives me a 0. And then I get both a negative 2 and a positive 2 for each of the factors, for the x plus 2 and the x minus 2. So if this was from part one, we would be done. You know, that's all I asked you guys to do for part one of this section was just that, find the critical values. What we're going to do for part two is we're going to use the critical values and decide whether each one is a local minimum or a local maximum or neither. And to do that, we're going to use the number line. So let me draw the number line now. I'm going to put 0 right in the middle. Here's positive 2. Here's negative 2. And those, the reason I marked those numbers, those are our critical values. Those create our intervals. So what I have to do for each interval, I have to go back here to this function, f of x, pick a number and plug it in. So for my first interval, I can basically pick any number less than negative 2. I could pick negative 2 or smaller. I'm sorry, negative 3 or smaller. I usually like to kind of stick close to the dotted line, so I would probably do negative 3. So let's find f prime of negative 3, which would be 4 times negative 3 cubed minus 16 times negative 3. So let's see, that would be negative 27 times 8 is negative 108. Plus 60, or plus 48 actually. Now what I notice here, I notice the answer is going to be negative. I have a bigger negative number plus a smaller positive number. I don't even really care what it comes out to. Once I realize that the answer is negative, I'm just going to put a little minus right here because the derivative is negative in that interval. Okay, for the next interval over, I would definitely choose negative 1. That's really the only whole number in there. So let's do f prime of negative 1. That would be 4 times negative 1 cubed minus 16 times negative 1. That would be negative 4 plus 16. That one's going to be positive for sure. It ends up being positive 12, but I don't even care about the 12. Once I realize it's a positive number, that's all I'm looking for. Okay, the next one I'm going to choose is positive 1. And that would be 4 times 1 cubed minus 16 times 1. And that would give me 4 minus 16. That one's negative 12, so I'm going to put a minus right there. And then for my last interval, again, you can pick anything bigger than 2. You can pick 3 or 10 or 1,000,000, doesn't really matter. I'll go ahead and stick with 3. So that would be 4 times 3 cubed minus 16 times 3. And that one's going to be 128, or 108, sorry, minus 48. It's the opposite of the negative 3, but it's definitely a positive number there. All right, so we got our plus minuses. I'm actually going to erase that word because I'm going to need a little bit more space here. All right. Now, what's happening here, if you want to think about the graph itself, every minus means decreasing, every plus means increasing. So you get this graph, and now you can see the shape of it. It's decreasing and then increasing and decreasing and then increasing. It's almost like W-shaped. So what I can see is I have a minimum here and here, and I have a maximum up here somewhere. Now, what I want to do to finish the question, this is why I erased, why I said I need a little bit more space. So for my local minimums, what I found is the x value of each one. So I'm going to have one at -2 comma something and 2 comma something. And my local max is going to be at 0 comma something. I found the x value, but I want the point. So what I need to do now is go way back to the beginning, plug those numbers in, and see what the y value for each one is. Now I'll start with the maximum because zeros are easy. If I plug in 0 for those x's, they all disappear, and I just get that 11, that constant term on there. I get 0 minus 0 plus 11, which is 11. Now for the rest of them, we'll have to do a little bit of work. So let's do the positive 2. Positives are a little easier. If I go 2 to the 4th minus 8 times 2 squared plus 11, that would be 16 minus 32 plus 11, and that would be -5. So that was when I plugged in positive 2, so I'm going to get a -5 right here. And we'll finish it out by doing the same thing with the -2. -2 to the 4th minus 8 times -2 squared plus 11. It's actually the exact same thing because those are even exponents. It still comes out to positive, negative. So yeah, we're going to get a -5 for both of them. And that was an 11 there. So that's how that question worked out. We over here, everything on the left side of the screen was exactly what we did in part 1. The right side of the screen is the rest of the first derivative test. So that's where you do the number line. You test numbers in the derivative to see whether your intervals are positive or negative. You use those intervals to determine whether each critical value represents a maximum, a minimum, or neither. And then once you figure that out, don't forget there's that one extra step at the end. We found the x values of the minimums or the maximums, and, but then you need to find the rest of the point. All right, so let's see. All right, even though this is getting to be a little bit of a long video, I'm going to do one more example for you guys. Same question, we're finding minimums and maximums. This time our function is 1 over x squared. Now, before I copy the question down, if we're going to take the derivative, I probably want to switch that to a negative exponent. 1 over x squared is the same as saying x to the -2. And the reason I did that is because now when I find the derivative, f prime, instead of doing quotient rule, I just do power rule. I multiply by -2, I subtract 1 from the exponent, which gives me -3, and I get -2x to the -3, or let me rewrite it. That could also be written as -2 over x cubed. Now, this thing only has one critical value. The reason I rewrote it as -2 over x cubed, I want to show you that concept of having a rational function, top and bottom. Basically, when you have that situation, you kind of split it in half. You say, wherever the top equals 0, that's where the function equals 0. And wherever the bottom equals 0, that's where the function is undefined. But those are both critical values. Those both count. Now the first one, -2 doesn't equal 0. There's no variable in that. -2 just doesn't equal 0. So you get no critical values from the top. What that means is we only have one critical value, and that's x equals 0, which makes our work nice and easy on the number line. When I draw in my number line, 0 is the only critical value, so there's only two intervals. So basically what I have to do is plug in one positive number and one negative number and see what we get. So let's do that. I'm going to plug in my numbers right here. This is f prime. So let's say I pick a +1, and I'm seeing what happens on the right-hand side over there. So if I plug in +1, I get -2 over 1 cubed. That's a negative number. It's -2 over 1. So we get negative. That was when I plugged in the positive that was on the right. Now if I plug in a negative number, I get -2 over -1 cubed, and that would be -2 over -1. That's a +2. So I'm getting positive over here. So what we have is a function that is increasing and then decreasing. Now what it looks like to me is I have a local maximum at 0. But if you remember the last slide from the notes, I warned you about something, and this is actually an example of that. I said a critical number can only be a minimum or a maximum if there's actually a point there. Now if you try to figure out the point, 0, something, and you go back to the original function, which if you look at the bottom, it's 1 over x squared, what you get is 1 over 0 squared. That's undefined. Can't have a 0 in the denominator. So that is not, it looked like a maximum, but it's not. It's not a local maximum. What it actually is a vertical asymptote. If you look at this graph, it looks like this. You have a vertical asymptote here in the middle, and the graph does something like this. So if you think about it, yeah, it's increasing until it gets to 0, and then it's decreasing once you pass, but it's not a maximum. Those two things never actually meet at a point that is a maximum. It just keeps going up forever. So be careful on that. You'll notice anyways, it's not something where you have to really think about. You notice it at this step right here. When you're trying to find that value of your minimum and maximum, if you plug in the number and it comes out undefined, then it means it wasn't actually a minimum or a maximum.